Today we'll be talking about modelling influenza epidemics using the SIR models. Influenza is an infectious disease that can spread rapidly amongst populations in bursts known as epidemics, or across wide areas known as pandemics. Epidemics relate to a contagious disease that spreads between people in one region. A pandemic occurs worldwide and across many countries. Two mathematicians, Kermack and McKendrick, developed a mathematical model to explain how influenza spreads throughout a fixed population, with the fixed population being no births or no deaths. Modelling the spread through a population to determine the magnitude of epidemics and how long before it deteriorated or wiped out the population is what they were trying to figure out. They did this in an attempt to help minimise the frequency and intensity of epidemics by showing the rise and fall of infected. The next question we have to ask is how this can be converted into a mathematical problem. According to Weinstein, an SIR model is an epidemiological model that computes the theoretical number of people infected in a closed population. The real-world problem has been converted into the mathematical problem by representing the number of susceptible people, number of infected people, and the number of recovered people as S, I, and R respectively. This is how we get the name the SIR model.
Within this SIR model, the S equals the number of susceptible population who are currently healthy, never had influenza before, and are not immune to it. Whereas I equals the number of infected population, and R is the number of recovered population. So people who are immune and will not get sick or infect other people. By breaking the population into a three-group setup, it is possible for us to keep track at the rate at which these populations are going to change. Where we can say S prime, I prime, and R prime is equal to the rate at which the SRI model changes. Whereas moving from S population to I population, it's the amount of population that gets sick, and moving from the I to the R is the amount of population that recovers. We're going to assume that every day a fraction B of the population will always recover. We can represent this with R prime is equal to B times I. And if we assume that the influenza runs for 2 weeks, we can suppose that every day 1/14 of the affected population will essentially recover. And the rate at which a population gets sick is proportional to the number of people who are S and also to those who are already I. The rate at which population gets sick is equal to A times S times I, proportional to the number of people who can get sick, S, and proportional to the number of carriers, I. Moving from S to I is the rate at which S is going to I, so it will equal A times S times I. And the rate at which going from I to R is B times I. The rate at which S is changing is a negative value because the population stops being susceptible to the disease, whereas S prime is equal to negative A times S times I. The rate at which I is changing is the rate the population is getting sick, minus the rate at which they are recovering, which is equal to I prime, which I prime equals A times S times I minus B times I. And the rate at which R is increasing is the rate the population is recovering, so R prime is equal to B times I. A is equal to transmission coefficient, which is dependent on the conditions, and B is the recovery coefficient, depending on the disease itself, whereas in this situation we're looking at influenza.
So basically what I'm going to be talking about today is the basic reproduction rate, and that is basically a measure of how fast or if at all an infection might spread through a population. So it's usually denoted as R0, and it's the average number of new infections generated from one primary infection, so i.e. new infections over initial infections. So this is a lot easier to see if I had a visual rep. So basically what I've done, I've created a scenario where there's 2 infections present in a population. And let's say, for instance, we start off with 4 people in each category at the beginning of the period. And let's say 2 weeks later we came back and we found 2 new infections in category A and 8 new infections in category B. with their respective R0 values being 0.5 and 2. So basically you can see that the infection A is on the decline and the infection B is almost doubling. So what this means is that, generally speaking, an R0 value greater than 1 means that the infection will slowly die out, as it would in infection A, and an R0 value greater than 1, which means that the infection will spread and an epidemic might ensue. So obviously ways to prevent this could be obviously through blocking transmissions. So this would mean isolating patients and ensuring healthcare workers, i.e. doctors, nurses, are wearing protective clothing when intervening with infected patients. And also a little more controversial one is obviously to reduce the susceptible population and in turn to reduce the R0 value. So that's done by obviously vaccinations. So basically vaccinations have been around for a while. They were used to eradicate smallpox in America and to reduce the prevalence of measles by up to about 95%. So yeah, it still stands today that mass vaccination is the most efficient method of preventing and controlling epidemics.